Number 14 in an introductory class in electricity and magnetism. And what I'm describing in this lecture is just some examples of using the idea of potential. Um, so these aren't really learning outcomes. They're just sort of examples of doing physics associated with potential. And the examples here vary quite a lot. It's going to start off with doing some calculus, like actually doing some math, and being very careful about the mathematics. Um, and it's going to be an example that I show you where um, it's harder to do a problem with the by using the electric field than by using the potential difference. And it's kind of cool. Like the potential difference, this thing called capital V, is a scalar function. So there aren't three components of a vector to integrate for like you would have to in the electric field. Um, and also the potential difference is a quantity related to energy, which is a very physical thing or concept to talk about. Um, and what's really interesting is there are guarantees that this sort of energetic concept to calculate can be calculated quite easily because you're guaranteed a path independence in the calculation. So this is a big deal. It Yes, it does not mean that calculating the potential is always the way to get started, but it does mean that in some cases it might give you a shortcut uh, to solving a problem. So yeah, in order to make that decision, honestly, you need to have some wisdom, and you get wisdom from having lots of experiences. And the way you gain lots of experiences is by practicing and doing homework. The truth is you're barely going to learn anything from any of these lectures, or watching Khan Academy. Yeah, you gotta learn by doing. All right, I've said that before. You know it in some sense, but yeah. Okay, so moving on. I'm going to do some practical exercises with the potential when thinking about the shell theorem. So we're going to calculate how the potential changes or does not change in the cases of using the shell theorem, and also thinking about uh, how special conductors are. And we're going to get an idea that I'm not sure why I don't see it that often in books, but this notion of an equipotential volume. Um, there are these equipotential surfaces that we described or thought about in an earlier video that you can draw when you're thinking about field line diagrams, electric field line diagrams. Yeah, so I'm going to show you an example of entire volumes that have the same potential, not just a two-dimensional surface, but a three-dimensional volume. This will show up in the shell theorem, and it also shows up thinking about conductors. And the idea or the point is that there's an entire volume in the shell theorem that might have electric field equal to zero. And whenever you do integrals with the electric field through a volume where um, it's zero, then there is no accumulation of, for example, a potential difference. Same thing happens inside conductors. Um, yeah, so I'll describe that through the bulk or volume of a conductor, in the material of a conductor, the potential remains the same everywhere. All right, so yeah, this is especially useful when you start thinking about conductors as wires or charge collection plates, like in a device referred to as a capacitor. Okay, so, and then I'll end by giving a very loose, this is a keyword, it's a somewhat mathematical, maybe kind of very hand wavy way to think about how strong is an electric field when all you know is potential difference and distance, right? Yeah, so you can make a judgment call. It's kind of like a loose judgment call. Yeah. Okay. Um, that's the lecture. So, as a first example of dealing with the electric potential, let's calculate for a uniformly charged disk. So this is not a ring, but it's a disk. It's a two-dimensional sort of surface with radius 5 centimeters and a uniform charge density throughout an area. So this is a charge per area of negative 10 nanocoulombs per centimeter squared. So this is a negatively charged disk throughout its area. And this disk is in the XY plane. I sort of drew that there. It's not a great drawing, but this is meant to be the disk. And it's circular. It's a circular disk. The question is what is the electric potential along the z-axis? So we can imagine at different heights z above the xy plane, what is the potential? Okay, so the strategy of doing this at some point is going to involve using an answer we already know. And the thing that we're going to use is that we already know the potential of a ring, a uniformly charged ring along z-axis. The answer to that is actually this. It's the potential as a function of height along the z-axis is equal to, it turns out it's just the charge of the ring. So this is the net charge of the little ring divided by, looking at a separate piece of paper because I wrote it down elsewhere. Yeah, so it's divided by 4 pi epsilon naught times the radius squared plus z squared. So this is the radius of the ring, all raised to the 1/2 power. Yeah, so this turns out to be the answer for a ring, right? Yeah, so let's use this to calculate the potential. The idea is the disk is just a bunch of rings, right? So this disk is equal to a small ring plus a slightly bigger ring plus a slightly bigger ring plus dot 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 plus finally the outer edge of our ring, right? So let's say this is the outer edge of the ring. So this is from a ring of radius 0 all the way up to a ring of radius capital R 5 centimeters. So we'll go from 0 to 5 centimeters. And so this R variable is how we are going to range over the charge distribution, right? And what we'll say is that each of these rings contributes a small piece of potential, right? And then the answer to the potential of the whole disk is using the superposition principle. So we'll superpose the potential to get the disk. So it's the superposition principle. All right, so
So let's keep going with that. So we're going to use this ring idea. So the potential, let me write it down again. So here is our little disk, and we're a distance z above the disk in the plane somehow. So let me indicate that this is a disk, and we imagine little rings of radius r, and we're just going to imagine a whole bunch of little rings all contributing a potential at z, and we can just integrate to get the answer for the total potential at z. So we have this thing. I wrote it down on the previous page. So the potential of a ring at a height z along its central axis of symmetry is equal to the charge of the ring divided by 4 pi epsilon naught, the radius of the ring squared plus z squared 1/2. And we're going to convert this to a small piece. And the way we say that is there is a small contribution to the potential of the disk, right? At a height z, and it's equal to the small charge of a ring of radius r divided by 4 pi epsilon naught, the radius of the ring squared plus z squared square root. So we need to figure out how to write down the charge of a ring in terms of things like r and an angle phi, and also the area charge density sigma. So how do we do this? Well, first thing that I would do is, if I was you, is I'd draw a picture. So a picture. So the picture looks like this. We could even wander up in here. So yeah, let me redraw it. So the picture, this is the entire disk. Here is the central axis of symmetry. And here is a ring. And this ring actually has a small thickness, right? Because we're going to take a whole bunch of small thickness rings and add them up from radius 0 all the way to radius capital R. Right. So let's look at this little ring. It's got a radius r, and if I look at this little ring, I can pick out a small element of charge, and this little tiny element of charge has a thickness dr, right? That's from the inner side to the outer side of this little ring, so that's a thickness dr, and then it's got a width that is r d phi, where phi, d phi is a small angle that sort of points out the left and the right hand sides of this little rectangle of charge, right? And there is a small amount of charge that sits there. There's a small point charge, right? Because it's all located in this small point within a dr out in the radial direction, and within an r d phi in an arc length side to side. And that small amount of charge is sigma times the area. So there's a small amount of area here that's dr times r d phi. So I just need to multiply a small amount of area times the charge per area, and I'll end up with a small point charge worth of charge sitting there. So this is sigma r dr d phi, right? So that's the charge of a point, but I want the charge of the entire ring. So I'll get the entire ring if I figure out, so the charge of the ring is going to be the integral of all the point charges if I go around the ring. And so the integral from, if I go all the way around the ring, which means just go all the way around the clock, right? All 2 pi radians. The thing I'm integrating is sigma r dr d phi. That's the point charge, and I'm going to add up all the point charges around the ring, right, and get the charge of the ring. So here is the charge of the ring, and what's interesting is I have this small amount of charge on a ring, so this is infinitesimal, is the result of one integral, right? Normally you get a finite value as the result of doing an integral, but really this integral only integrates in one of the 2 directions. So we're left over with an infinitesimal with respect to the other direction, which is the direction r. That's kind of a weird way to put that stuff, but the result of only doing one integral, when really I'm talking about a 2-dimensional sort of finite or infinitesimal element. So the integral is simple. It's 2 pi sigma r dr, right? So because r is independent of phi. So now I've got the charge of a ring, and I can say that there is a small piece of potential up here for the disk, right? Which is equal to, actually, let me say that if I integrate up all the small contributions to the disk's potential, I'm going to get the full value of the disk's potential. So what I need to do is figure out how to get the small potentials for the disk, and this is how I get it. I have to do the small charge of a ring of infinitesimal thickness, and then I divide by 4 pi epsilon naught, the radius of the ring squared, the height above the center of the ring squared, all in a square root. So here's the charge of the ring right here. It's an infinitesimal charge, and I'm going to have to think about how am I going to range over the whole disk by thinking about individual rings. So the individual rings have this infinitesimal charge, 2 pi sigma r dr, and then I divide by 4 pi epsilon naught r squared plus z squared raised to the 1/2 power. And I can see that this is my ranging variable. So this just says take r from 0 to capital R. So it turns out that this integral is easy. And the answer, it turns out, it looks like this. It's 2 pi sigma, it's just the first stuff here. The derivative of the inside of this piece of, or this denominator happens to be on top, so this is super easy to integrate by parts, or just you could just sort of guess the integration. 2 pi sigma over 4 pi epsilon 0, and then it when you it'll look like this. It'll be r squared plus z squared. Whoops. Yeah, minus z quantity, like this. So this 2 pi sigma over 4 pi epsilon naught multiplies this. This is sort of the integral without the constants. Okay, so this is the answer to the potential of the entire disk, right? All the radiuses and all of the angles. So it's the entire disk, and it is a function of height above the center. Yeah, and so we've got an answer. So the original question was, what is the potential along the z-axis? And I've got these values, right? 5 centimeters and negative 10 nanocoulombs per centimeter squared. And you can see that you can just go and plug in, remembering that 4 pi epsilon naught underneath 1 is about 9 times 10 to the 9th. It's newtons meters squared per coulomb squared. Right, so yeah, you can calculate this out. So I realized I made a mistake. I forgot to include the square root here. So yeah, so it is an easy integral, but yeah. Anyhow, let's study this result for a second. So I'm just transcribing. You can see that I'm about to do that. This is what I'm going to transcribe. So the potential at distance z away along the central axis of symmetry of a uniformly charged disk, right? Lots of caveats or specificness. Is this expression here, r squared plus z squared raised to the 1/2 power. I'm going to, well, I'm going to write down what we have and then talk about why we've got to actually be a little bit careful and include the absolute value bars around the z. So if you look at this function, or I mean, here's the original problem. So I've got this charged disk of radius r, uniform charge density sigma throughout the disk. And this was the direction of the positive z. And then below this is the direction in minus z. And you can see that actually, without the absolute value bars, the potential for negative z will be different from the potential for positive z. But we actually want this potential to be an even function of z, honestly, because the potential, say, 5 centimeters up above the plane should be the same as 5 centimeters down below the plane. Without the absolute value bars, this first term is even in z, but the second term is going to be odd in z. So yeah, you can see that we need to make sure that v of z equals actually the same thing as v of minus z. That is, it's even in z, and this is the way you make it even in z. So this is the best way to write down the potential along the z-axis. Another thing you can do to explore this is to ask, well, what is v at 0? This is an interesting question. So nothing about the prefactor depends on z, so it's just all the same. And of course, you can see that this is the same thing as sigma over twice epsilon naught. You can divide the 2 pi by 4 pi. That's 1/2. And then when z equals to 0, it's just the square root of r squared. So this looks like this, right? So it's funny because we're asking what is the potential at the dead center, and the electric field at the dead center, symmetry-wise, right? The electric field at z equals to 0 should be equal to 0, and this is by symmetry. The idea is a test charge at the center is going to, for example, be repelled from the right-hand side of the disk as much as it's repelled from the left-hand side of the disk. And so the test charge at the center is feeling forces on it such that the net force is always 0. Yeah, so this is interesting. The electric field equals to 0, but the potential there is not equal to 0. And the way you can understand that is this has got something to do with the amount of work, right? The amount of energy, right? Work per charge required to move that charge in from infinity to there. So even though you're, say, fighting an electric field all the way to the center, by the time you get to the center where the electric field is 0, you've still done a whole bunch of work throughout a space where the electric field is not 0. So the electric field out here is not equal to 0. But the electric field down in here is 0. Yeah, so yeah, we're just doing some exploration. The electric field out here for places where x and y are not 0, we did not calculate this. So the reason I bring this up, so the electric field where x and y are not equal to 0, we don't know how to write it down. I don't know its functional form. It's probably a pretty interesting function of x and y, and still a function of z, honestly, right? And also the electric field somewhere out here in the disk where x and y aren't 0 but z is equal to 0, the electric field here is not 0. It's likely not 0, although I didn't calculate it, but it's not going to be 0. So let me show you something that we can do. So here is our picture. So let's say that this is a position called A on the z-axis, and this is a position called B on the z-axis, and B is a little bit closer to the disk than A. And we imagine a path and we want to know what is work required to move a test charge Q from A to B. What is the work required to move a test charge Q from A to B? And actually, specifically, it's along the red path over here. So this is this red path. Well, in order to do this problem, the work equals Q times the change in the potential from A to B, right? And you know that this is Q times V at B minus V at A, multiplying on the quantity. So this is the potential difference between B and A. That's what this delta V from A to B is. And this is super easy to calculate. This is just Q times the potential, this expression up here, evaluated at Z equals to B, minus the potential at Z equals to A, right? And then you just multiply by whatever the test charge is. So what's interesting is this is the answer even along the red path. And so imagine if we wanted to calculate the work the hard way. The hard way is to actually think about what is the external force necessary. And the external force necessary, so this is the work done. We'll go from A to B using some external force to do work along small displacements along the red path. So we're going to go from A to B along the red path. So we're going to use little tiny ds vectors. So here's a few of them. Here is a ds vector. Here's another ds vector. Right? You can see. So these little ds vectors are out here. And the way that we're going to do this work, I've mentioned this a few videos ago, or maybe just one video ago, is we're going to use an external force that exactly matches the electric field of the disk, right? And the electric field of the disk is a function of x, y, and z, and we're going to integrate this dotted with ds's that take us along the red path from A to B. So the problem is, I alluded to this up here, we don't know how to even write down the electric field as a function of x, y, z. So doing this directly, this is the hard way. It's actually, we don't have enough information to do this. But because of path independence of delta V, we don't have to. We don't need to do this particular path integral. It's just, you just do this right up here. It's Q V at B minus V at A, quantity, and we're using path independence. Yeah. All right. So the next thing that I'd like to describe is thinking about the potential and the shell theorem together. So the shell theorem is about spherical shells. So uniformly charged spherical shells. So uniform charge distribution, and the shell needs to be spherical in shape. And you'll recall that the electric field inside shell equals 0, and the electric field outside equals the electric field of a point charge centered at center of shell. Something like that, right? So this is the shell theorem for the electric field. But if we think about the potential, so let's draw this shell. So here is a spherical shell of uniform charge density, and I'm just going to put down a coordinate system. So for example, this is y and the x direction, and so the electric field as a function of x, so just at coordinates along the x direction, the electric field actually has a magnitude. Let's say that this charge that's smeared uniformly over the surface is, say, positive. So yeah, so just as a something concrete to say, so this electric field can be written down piecewise. It's 0 for positions x that are smaller than the radius of the sphere. So let's say this is of radius r. And it's outside, it'll be the charge q over 4 pi epsilon naught x squared, right? Because we're just staying on the x-axis. If we wanted to go along the y-axis, be a y squared. Okay, so that's that. So the potential, though, so if you graph to the electric field is interesting as a function of x. The position r is interesting, and the electric field has a magnitude that grows as you get closer to the sphere. It grows in this 1 over x squared, so not parabolic, excuse me, but it's a 1 over sort of x squared growth to r, but r is not an asymptote, it doesn't blow up. It becomes 0, right? So E equals to 0 inside, and then outside the electric field has a magnitude that goes like 1 over x squared, right? So inverse square law. But the potential is different. So we're again thinking in terms of positions along the x-axis. The potential has a qualitative change also at x equals to r, but the growth along the x-axis as we come in is slower, right? It's slower because it's going to be like 1 over r. So the potential is going to grow like 1 over x, right? Because, yeah, I think you know. But then what's interesting is the electric field is equal to 0 inside. So whenever I want to study potential differences, if I stay inside, like for example from say position A to position B, where A and B are inside the shell, then when I integrate minus the electric field dotted with displacement vectors that take me from A to B, where A to B are all inside, this is only ever going to be 0. That is, if A and B are inside the shell, right, we could imagine this is A is on the inside and, for example, B is also on the inside of the shell. There's just never any difference anymore. So V is constant inside the shell, but outside the shell, V diminishes like 1 over x as I go further and further away from the shell. When finally I get to x equals to infinity, the potential at infinity is equal to 0. Yeah, that was our choice in a sense. But anyways, so something we can take away from this is inside the shell, since the electric field is 0, there is no potential difference between two places that are both inside. This is what's referred to as an equipotential volume, right? That is the entire volume of the shell, the interior of the shell, has the same value of potential. It's an equipotential volume. We studied equipotential surfaces before when I was, like a video ago, when I was describing to you the relationship between the field lines and equipotential surfaces. But here is an equipotential volume. The entire volume's the same value of potential. All right. So, an interesting thing to wonder about is, what about conductors and potential difference? The special thing about a conductor is no matter what shape it is, and also no matter the charge distribution on its surface, right? So I could have pluses over here and minuses over here. But no matter the charge distribution on its surface, or even the net charge of the conductor, E is 0 inside conductor material. And so if E is 0 inside conductor material, that means that the interior, or actually maybe not the interior, but let's say the conductor material is also an equipotential volume. And the reason is because the electric field is zero. So whenever you do the integral of the electric field within the bulk or volume of the material, you can never accumulate any extra potential, right? Because there is no potential differences within the material of a conductor. This is kind of a really big, useful thing to realize, especially for the future topics in a class, because you're going to start talking about circuits. And circuits are systems of electrical elements or things that can have electric charge, that can conduct electrical currents. And this is a useful thing to keep in mind because it helps you think about potential differences amongst circuit pieces, parts of a circuit. So what I'd like to talk about next is what I like to describe as a very loose way to think about the relationship between electric field strength. So this is what I'm talking about is the strength of the electric field, the magnitude of the field, and the potential difference. So the potential difference is this delta V. What I've written down is the exact relationship. If I have an electric field throughout space, the potential difference is the integral from one place to another place. So this is the potential difference between those two places of the negative of that electric field dotted with displacements along any path that I choose that goes from a place A to place B. This is exact. This is not loose at all, so not loose. A loose way to look at this, though, and it can be a useful thing when you're just thinking about problems or thinking about how things need to go, sort of a back of the envelope style way of thinking about things, is to look at this and realize that what makes this complicated is when E has a variation in space, right? So E is a function of these position coordinates. And the ds vector and the electric field might have relative directions that are interesting. You know, they're not always parallel or perpendicular or anti-parallel. It's, you know, the angle between a small segment along the path and the electric field can be 10 degrees or 50 degrees or 218 degrees, all kinds of angles. But if you get a little bit loose and just say that this thing is kind of like taking the electric field's strength on some average way, right? So some averaging, and then just multiplied by the distance between A and B. So let's call this, say, so multiplied by the distance between A and B, right? That's what the integral is going to do, is accumulate up this dot product for us along small distance elements from A to B. So some average value of E over the distance, and you can say that the potential is kind of like the electric field's strength, right? The magnitude, so in an average sense, just multiplied by the distance, D. So something like this. So for example, what if I know that this object and this object, let's say that this thing is sort of negatively charged and this thing is sort of positively charged, not necessarily the same amount, but a positively charged object tends to be a higher value of potential than zero. So let me just ballpark something. So this object compared to infinity, say is, or let's say this is a conductor. So this conductor is an equipotential volume, so all throughout the volume is the same potential. Let's say that the potential of this conductor that's positively charged is positive, say 5 volts, right? And this conductor, which is negatively charged, has an equipotential volume. So this is a place. Let's say that it's more charged than that thing, but in the negative sense. So I don't know. Let's give it negative 10 volts, right? So if you went and thought about electric field, right? Field lines are going to leave from this conductor, right? Basically in all directions. And field lines have to go into this negatively charged conductor. And so the way that's going to look is something like maybe this or something, sort of dipole looking, for example. Interestingly, though, this has got it. I drew 4 minus signs compared to the 3 pluses, so maybe actually some of the field lines don't come from that plus conductor. They come in from very, very far away. So, right? And yeah, so let's say that this is the rough idea. So, roughly speaking, there is an electric field maybe in here that we could begin to give an approximate strength to, right? And so let's say that this 5 volt conductor and this negative 10 volt conductor are separated by a distance equal to 1/2 of a meter, right? So this is a distance. And so I've got an electric field that on average between these conductors, which are 15 volts of difference, so delta V equals 15 volts. The distance between the conductors is 1/2 of a meter. This is kind of interesting. Is this the distance between their centers or their outsides or their insides? Well, the answer is I'm going to use an approximation, so I really don't care. This is roughly how far apart they are. You might say that this is the scale of the distance between them. It's on the order of 1/2 a meter, whatever that means. This is a very loose way to think about the relationship between electric field strength and potential difference. And so you can see that delta V divided by capital D, so the distance between the conductors who have a potential difference between them of whatever it is, in this case is 15 volts, gives rise to, not an equal sign. It's a goes like. It's like a similarity sign. Gives us some sense of the strength of the field on average around or in between the conductors, in between these potential difference, or this potential difference. So when you do this operation, you see that the electric field has an average-ish value of about 30 volts per meter, right? A volt is a joule per coulomb. So 1 volt is 1 joule per 1 coulomb. And a joule, a nice way to understand it, especially if we're thinking about this electric field strength, which is related to force, right? The nice way to think about joules is not kinetic energy, but instead in terms of work. So 1 Newton times 1 meter, that's what a joule of work is. You divide by a coulomb, and you can see that here, so 30 volts per meter is 30 Newton meters per meter. Oops, and I forgot the coulomb, right? The coulomb is down there, so that's here. coulomb. And so this is 30 newtons per coulomb. So it gives you a kind of a scale or a size of the field in between. Of course, the field gets stronger as you approach one of the conductors. In this case, the field is strong towards the conductor, gets a little weaker, then gets strong again towards the conductor. You can tell that because the field lines squeeze back towards each other, so the density of field lines is a little bit stronger towards the conductor, and they spread out, so it gets weaker, but then they squeeze back together and get stronger again on the other side. But in some sense, a description of the strength of the electric field in between the conductors is about 30 newtons per coulomb.